Hey everybody. This week we are on Unit 10. We're getting close to the end of the course. We're going to talk this week about one of the other classical assumptions, that of the problem of serial correlation. So remember, one of the classical assumptions is that each error term is uncorrelated with an error term at another point in the data set. So we're going to talk this week about what do we really mean by that and when would it be violated. Turns out it's often violated when we have time series data. So we'll have to figure out a strategy how to deal with that. So in the first lecture this week, we're going to talk about what happens when you have autocorrelation and how you can remedy that. The slope coefficients remain unbiased. So OLS is still good for getting you an unbiased slope coefficient, but the variance estimate, once again, is biased, and we need to fix that or we'll get wrong t-statistics and p-values. Then next lecture, we will talk about how to test for serial correlation. So this week, the pattern is really similar to last week. We start off by talking about the violation of the classical assumption, what it does to our estimates, how to remedy it, and then next lecture, we will talk about how to test for it. So buckle up your seatbelts and we'll get going. All right, so our topic today is serial correlation, which is also called autocorrelation, and it's also called autoregression in some cases. And it all pertains to classical assumption 3. So assumption 3, which is that the covariance of any of those two error terms equals 0 for any two distinct error terms. Now, this assumption is often violated in time series analysis. So if it's going to fail anywhere, that's where it fails. Usually violated in time series. Now, it can also be violated in cross-sectional analysis, but we're going to focus on the time series case. So if we use time series notation, then instead of the little I and j subscripts, we would write, say, xt, where t equals 1 through to the end of the sample, which we can write capital T, and yt, and then those little error terms will look like that. And since we have to distinguish between the error terms at different points in time, we can write covariance of the error term at time t and the error term at time t minus j. And we're going to assume that that is not equal to 0, so we're violating the assumption. And that is for j not equal to 0. So if j equals 1, then that means it's the error term for this period and last period. If j equals 2, it's 2 periods back, and so forth. So with time series, it means we're indexing the observations in time. And in economics, we often use time series data. So you have gross domestic product for 1981, 1982, 1983, and so forth, price indexes, and all the rest. And so when you have data that's ordered in time, it makes perfect sense to think that there are going to be patterns that are correlated over time. So what happens if assumption 3 is violated? So if assumption 3 is violated, Well, one of the points, and the book doesn't really go over it, doesn't discuss it in any detail, but it's, as with the heteroscedasticity case, OLS is still unbiased. So OLS is still unbiased, but it is no longer blue. So let's pop back over here to page are we on? 68 is the magic page. The idea that OLS is unbiased, so that proof is on page 68, which you've worked through a few times. And the main thing is just that in order to do the proof, we don't have to assume that the errors that have no positive covariances across time. In other words, assumption 3 is not part of that proof. So if assumption 3 doesn't hold, that proof still goes through. So we don't need to go through the proof again. We can just say, well, we didn't need assumption 3 for the proof that OLS is unbiased. So we don't need that. But it is going to be the case that our variance estimate is biased. So what we do need to prove is the variance estimator is biased. So to do that, we're going to assume a specific form of the autocorrelation. Assume a specific form of autocorrelation. We are going to suppose that the error term at time t is equal to the error term at time t minus 1 times a coefficient we'll call rho plus another random variable, u. And we will assume that u is the part that satisfies all the classical assumptions. So meaning, what does that mean? The expected value of u equals 0. The variance of u equals sigma squared. And the covariance of u at time t and u at any other time equals 0 for j not equal to 0. So we'll think of u as u subscript t, not you personally. I'm not thinking about you. I'm thinking about u, this u. We'll think that it satisfies the classical assumptions. It's a well-behaved random variable. I'm sure you're well-behaved, but you're not a random variable. Well, I guess you are a bit of a random variable, aren't we all? But u satisfies the classical assumptions, and it is embedded in this function. So the error term in our regression model is going to be a multiple of last period's error term plus a classical error term. What we do is we call these white noise terms, or well, some of the geekier people call them independent and identically distributed random variables, but the jargon in statistics and econometrics is u is called a white noise random term. And white noise, it means that it's completely uncorrelated over time. It's just, it's the classical error term. All right, so this process, this random stochastic process, that is called the AR1 model. So I'll call that the AR1 process. And AR stands for autoregression or autoregressive errors. And this is an example of something called a stochastic process. I don't think he uses the term stochastic process in the book, and you don't need to memorize it or anything, but when we're dealing with time series data and you're thinking about there's some underlying mechanism that's generating the observations. It might be the stock market, for instance, is generating stock prices minute by minute. And there's a part of that's deterministic. It's whatever drives the prices, but there's also randomness in it. So we think of that as a stochastic process that's generating this series of observations. And there's an important property here. If it's a reasonable process, it should be non-explosive, meaning that a little deviation at one point in time doesn't cause the whole system to wander off to infinity. So if a stock fluctuates up in value at one point in time, it shouldn't be the case that that then gives rise to an unbounded process where it becomes worth trillions and trillions of dollars by the end of the day. Most things in life are non-explosive processes, meaning that a deviation at one point in time gets dampened back out. And so things revert to their starting point. And so that is called stationarity, or a stationary process. Stationary process, stationary stochastic process, reverts to a stable mean. There's more to it, but that'll do for our purposes here. A stationary stochastic process reverts to a stable mean. And so in this case, this requires that this rho variable has to be between -1 and +1. All right, so that rho, it would be okay if it's 0.5, but not okay if it's 1.5. It would be okay if it's -0.5, but not okay if it's -1.5. It's got to be bounded between -1 and +1. Otherwise, if it was greater than 1, as we'll see, a little fluctuation in u would eventually cause epsilon to go to infinity, plus or minus infinity. Okay, so let's get a little more notation going here, a slight change in notation. So let's say we've got epsilon t equals rho times epsilon t minus 1 plus epsilon, plus u t. Now I'm going to subtract s from each of these t's. And in a sense, all I'm doing is I'm shifting my observation s periods in time. So if s equals 0, then that's just the same as this expression here. If s equals 1, then this is epsilon t minus 1 equals rho epsilon t minus 2 plus u t minus 1. And if s equals 2, then epsilon t minus 2 equals rho epsilon t minus 3 plus u t minus 2, and so forth. So I haven't really changed anything. I've just added s in there and s can be any integer, and that way what you can see is that you can lag this process. You can look at the lag values of the process. Right, I'm going to switch to a new page. If you need to write that down still, pause the video, but here goes. All right, now let's start with this. We'll note that epsilon t equals rho epsilon t minus 1 plus ut. Now I just showed you that we could write another expression for epsilon t minus 1. We can write rho epsilon t minus 2 plus u t minus 1 plus ut. All right, so that substitution there I showed you on the previous page. And so then if we just distribute that out, that's rho squared epsilon t minus 2 plus rho ut minus 1 plus ut t. No minus anything. Well, we can also make a substitution for epsilon t minus 2. So that will be rho squared. And what's this one going to be? This will be rho epsilon t minus 3 plus ut minus 2. And then we have rho ut minus 1 plus ut. Okay, so this is the substitution that we made. And we can factor that out as well, like so. Rho cubed epsilon t minus 3 plus rho squared ut minus 2 plus rho ut minus 1 plus ut. Now it's t minus 0. I could actually write rho to the power of 0. Rho to the power of 0, ut minus 0, if we want to write it that way. And now you start to see a pattern here. So rho is rho to the power of 1. So here I've got rho squared and then t minus 2, rho 1, t minus 1, rho 0, t minus 0. And then I've got rho to the power of 3 in the epsilon term. So I might be able to just keep going in that same iterative way and get, let's say, rho to the power of 100 epsilon t minus 100 plus rho to the power of 99. Now we go to ut minus 99 plus dot 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 plus, and then we get to rho 1 ut minus 1 plus rho 0 ut minus 0. So I'm not going to do all those substitutions, but if I did, I would just keep going. It's just an infinite loop that I'm going to be in. However, I made this assumption about rho, which is that it has to be absolute value less than 1. So that means if you take any fraction less than 1 and you raise it to very high exponential powers, it goes to 0. So since the absolute value of rho is less than 1, then rho to the power of, I need something here, any old variable will do, but I don't want to use one I've already used, so I think b. I don't think we've used, oh yeah, we've used b. Oh well. Rho to the power of b goes to 0 as b goes to infinity. So as that 100 then becomes 1,000, becomes 1,000,000, as high as you like, rho to the power of that number goes to 0. So then epsilon t equals, let's just turn this around back to front. So we're going to do it this way. Rho 0 ut minus 0 plus rho 1 ut minus 1 plus dot 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 plus rho, what do we get? 99 ut minus 99. But then we could have kept doing the substitutions, and each time we do the substitution, you just add the next u term in the sequence plus, then, but instead of writing rho 101 et minus 101, I'm just going to suppose that I keep going with the rho and the u terms. And at a certain point, eventually, I don't need to bother writing that term because it's gone to 0. We've got rho to the power of 100 times something, but it's going to go to 0. And so the advantage of writing it out this way now is I can drop it all into a summation. So I have rho to the power of I ut minus I, where I equals 0 to infinity. And if I goes to infinity, then this part of the sequence disappears. It goes to 0. So I'm left with epsilon equals an infinite sum of the weighted past u values. So I started with this simple AR1 expression, and then I did this inversion through substitution, and I end up with another equivalent expression. So the AR1 model can be replaced with this infinite sequence of past values. And by writing it in this way, now the first thing I'm going to do is take the expected value, and that is going to be the sum of rho times the expected value of ut minus I. But it doesn't matter how many of these I add up in sequence because they're all equal to 0. So that was from the fact that this is a classical error term, has an expected value of 0. So even though I'm adding up 1,000,000 of them in sequence, it still equals 0. They all equal 0. We'll do the variance next. And to do the variance, I have to introduce one little mathematical trick, but using this summation is going to help us. So here's the little mathematical trick that I want to show you, and that is if you have a constant c, and c is strictly between 0 and 1. All right, so c cannot equal 1. It has to be less than 1. And it can't equal 0. It has to be greater than 0, but it can be between those two numbers. Then, if you take the sum from 0 to infinity of c to the power of I, that equals 1 over 1 minus c. So that's one of the clever little mathematical results for infinite series. If you're adding up that series, so let's say c equals is 0.5. That's an easy example. So then 0.5 to the power of 0 plus 0.5 to the power of 1 plus 0.5 squared plus 0.5 cubed plus and so forth equals 1 over 1 minus 0.5, and that equals 2. So that is a mathematical result. It's not actually all that hard to prove. It looks pretty magical, but we're not going to do the proof here. Now, what if we square C? Well, then the sum of C squared is just going to be 1 over 1 minus C squared. And because we could just do a change of variables, substitute in a different variable, which turns out to be C squared, and so that will hold. So with that in mind, let's compute the variance of our AR1 error term. So that's the variance of rho epsilon t minus 1 plus u, and that is the variance of, now remember that inversion that we did that turns this into an infinite sequence, j equals 0 to infinity, rho to the power of j, u t minus j. So that, well, let's see, we can take the variance inside the summation here. Rho j u t minus j. Now remember, that's a classical error term, so it's got a constant variance. But this is a constant, and we have to move it outside of the summation. But because we're moving it, move it outside of the variance. But when we take a constant outside the variance, we have to square it. So we've got j equals 0 to infinity, rho squared times, and that's rho squared times j, times the variance of u t minus j. And this guy right here is a constant. So we've now got j equals 0 to infinity, rho 2j sigma squared. I'll put a little u under there to indicate the variance of u is sigma squared subscript u. And then I can take that outside the summation, sigma squared u. And now I've got the sum of rho squared times j. And so then I can use that result. So that is sigma squared u over 1 minus rho squared. And so this works out to be a nice simple formula. You'll notice that t does not appear in this expression. What does that mean? It means the variance doesn't change over the sample, which means that it's a homoscedastic error. If t appeared somewhere in here, that would mean the variance is changing over the sample. But t does not appear, so we have homoscedastic error. So that's nice, then we only have to worry about one problem at a time. The autocorrelation of the error term doesn't induce heteroscedasticity. All right, now let me change the page and scribble that at the top now. So the variance of our autocorrelated error is sigma squared over 1 minus rho squared. Now you can see why rho could not be equal to 1 or greater than 1. So if rho equals 1, this variance goes to infinity. So if rho equals 1, then the variance goes to infinity, and that's what we mean by an explosive process. Okay, one little deviation and the variance is infinitely large, so your subsequent deviations can go off infinitely in in any direction. If rho is greater than 1, then the variance of epsilon goes negative. Now we're saying 1 minus some number that's greater than 1, and you can't have a negative variance. So for that reason, with the AR1 model, it only makes sense if rho is bounded between -1 and +1. And the covariance of two error terms equals, well, there's a whole bunch of math involved in this one. Just flip open the page. We are on page 141, and well, you can see there's a lot of scribbling, a lot of notation. So Professor Koop says, well, this covariance, it gets a bit messier, and then he goes, oh, this looks a bit messy, and down here, the derivations are somewhat messy. Messy. So let's not trouble ourselves with them at this point, because it reduces to a very simple expression. It reduces to rho to the power of s times the variance of epsilon. And that's nice when you have messy expressions that reduce to simple expressions. So that covariance has rho to the power of s. Rho, remember, is bounded between -1 and +1, so it does mean that the nature of the AR model, the autoregressive model with only one lag in it, is that these covariances go to 0 as you expand the time interval. So think of a recession year. For instance, this year, 2021 or 2020, we've got a recession due to COVID. That means next year will be below trajectory as well. But you go 50 years from now, and the economy is not going to be reflecting any influence of the COVID recession. Just as this year, we're not still suffering the effects of the Great Depression in the 1930s, or even the recession of the early 1980s. So the influence of a random shock in one period decays out and doesn't keep influencing things forever and ever, at least to a large extent. One of the terms that people use in analyzing these sorts of data series is that these series don't have long memory. So they have short memory. And again, you can think of, let's say, stock prices. If you have a stationary process in stock prices, then it means if a company has a bad quarter, it's not going to mean that every quarter from then on is going to be bad. They will recover, hopefully. Or maybe they'll go under, and then it is long memory. One bad quarter and they went under forever, but we don't expect that is usually the case. So that's the nature of our serial correlation. Let me just summarize a couple of points here. Serial correlation means, so the expected value of beta hat is still beta, so OLS is still unbiased, but OLS yields biased error variance estimates. The variance of our error term is no longer equal to this constant term that we were assuming, where sigma squared is the expected value of the error variances. Instead, the variance will equal sigma squared u over 1 minus rho squared if epsilon is an AR1 error term. Now, what if epsilon is an AR2 error term? AR2. It could be. That just means epsilon t equals rho 1 epsilon t minus 1 plus rho 2 epsilon t minus 2 plus ut. Well, we could go back and work out all the results that we did before. And as the book says, it will get messy. But we don't need to for this purpose. The form of the serial correlation can take many forms. You can have ARP, we'll call it. So you could have p orders in the lags. T equals, so then we have rho 1 epsilon t minus 1 plus dot 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 plus rho p epsilon t minus p plus ut. So it just means we expand out the function that determines the error terms. And this might apply in economic data, for instance, when there are seasonal effects. So if it may be the case that parts of the economy are important in the summer but not so important in the winter, so then if something exceptional happens one summer to the tourist industry, and then the tourist industry expands, and the next summer it may be a big season again because now they have more facilities. So so it may be that it's not just 1 month to the next, but it might be an autocorrelation 12 months apart. So we worked out these results for the AR1, the simple AR1 process. We're not going to work them out for all the others, or for the general AR process. What we'll just point out is that any of these means serial correlation, beta is still unbiased. OLS still gives us unbiased slope coefficients, but it gives us biased error variances. And these error variances now get much more complicated if we have p lags in our autoregressive process. Excuse me, I'm just taking a sip of my coffee there. All right. So that is the problem. How do we fix it? To fix this. Well, remember with heteroscedasticity, we worked through the GLS approach, and then we said there's this other approach called an HCE, or a heteroscedasticity consistent estimator. We're going to do the same thing. We're going to work through the GLS approach and how to estimate it, but then we're also going to refer to autocorrelation consistent estimator. So the GLS approach. So the GLS approach involves transforming the regression model so that the error term is now just u, that little classical error term. And then if you can transform your regression model that way, and then apply OLS, you'll get blue estimates. So let's start by writing down our basic regression model. A plus, alpha, because that's what the textbook uses. Alpha plus beta 1 x1 plus dot 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 plus, and then we'll go up to k regressors xt plus epsilon t. Okay, and we'll call that equation 1. And now we're going to take the lag, 1 period lag. Yt minus 1 equals alpha plus beta 1 x1 t minus 1 plus dot 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 plus beta k x k t minus 1 plus epsilon t minus 1. So same equation, I just lagged at 1 period. But now I'm also going to multiply through both sides by rho. So I just have to multiply a rho in front of everything. Okay, so lag 1 period and multiply by rho. And we'll call that equation 2. And then I'm going to subtract 1 minus 2. 1 minus 2. So that's going to be yt minus rho yt minus 1 equals alpha minus rho alpha plus beta 1 xt minus rho xt minus 1 plus dot 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 beta k x kt minus x kt minus 1 plus epsilon t minus rho epsilon t minus 1. Okay, what have I got here? How is this helpful? Well, let's look at this over here. So remember, epsilon t equals rho epsilon t minus 1 plus ut. That's in the AR1 model. So if I rearrange this and I have epsilon t minus rho epsilon t minus 1 equals u. So that means that this regression equation has a classical error term. If I define yt star equals yt minus rho yt minus 1 and xt star equals xt minus rho xt minus 1. And I do that for all the x's, so I'll add the little I in there. I equals 1 to k. Then yt star equals alpha star plus beta 1 x1 t star plus beta k x kt star plus ut, and this alpha star will be alpha minus rho alpha. So if that's my model, and I did OLS on this model, OLS would be blue, meaning I would get unbiased slope coefficients and they would have the minimum possible variance. The catch, and you're probably wondering this, is how can I construct these variables if I don't know what rho is? Well, we'll figure that out. We'll come up with a way of estimating rho. What I will point out is that this approach, it's nice and easy to figure out. It's intuitive. It does mean you lose a variable at the beginning of your data set, because you can't define this for the first row of your data set, for the first line of your data set, because you need the data from the period previously, which you don't have. So you can only do this starting from the second line of your data set. So we do lose a row. We lose one observation, basically, to do this. So there's a cost that way. To estimate row. Well, there's a procedure, and it goes like this. Regress yt on the x's to get the OLS residuals. All right, so you just do the regression as if you didn't have an autocorrelation problem, and you get the residuals, epsilon. Now we'll do this regression. We'll regress epsilon on epsilon t minus 1. So take the lag of epsilon, and we're just doing this regression here. Epsilon hat t equals rho epsilon hat t minus 1 plus some error term, and that yields rho hat. So we just get rho hat as a regression coefficient on the residual terms. And then we use rho hat to construct yt star equals yt minus rho hat yt minus 1, and then x is x lagged minus rho hat x. Oops. Scratch that. X I t equals rho. No, I was right before. Sorry. Don't know what's wrong. I was misreading my notes here. X I t minus rho hat x I t minus 1. And also we need to do no, we don't need to do anything with alpha. That'll be done automatically when we estimate the regression. So we're taking our estimate row, and then we're constructing estimated versions of these terms here. Oops, a row missing in there. I wonder if you noticed. You guys probably noticed that. How many other mistakes have I made along these lectures? And because I don't have a class in front of me to point them out. So there's supposed to be a row in there. So we're constructing estimates of these, just plugging in rho hat and then rho hat and rho hat. And we don't need to do anything here because that's just a constant. So the regression model is going to add the constant anyway. So then the fourth step is regress yt star on x1 t star x2 t star and so forth to xk t star, and this yields our GLS estimates. This is called quasi-differencing. So the textbook uses that term, quasi-differencing. If rho equals 1, that's just called first differencing or differencing. So if you take the first difference of a time series, you're just looking at the changes from one time to another. So if rho equals 1, then this is just the step value from xt minus 1 to xt. So that gives us our new coefficients. Now we could stop there, but we could go on. So we could use beta hat GLS to construct new error terms. So that will be given by yt minus alpha star hat minus beta 1 hat. Now we're going to use, I shouldn't have put a star on that because that's just going to confuse you. This is, we're just going to use the coefficients from step 4. So beta 1 hat, but I'm using the untransformed x's here. 1t minus beta 2 hat x2t minus beta k hat x kt, and that equals a new error term. I'll call it epsilon tilde. So what I've done here is I've taken my coefficients from step 4, just a regression, just get those coefficients, and then I construct a new set of estimates of the error term, and then use epsilon t tilde in step 2. All right, so I've gone up here now to step 2, and I get a new estimate of rho. And then now I use that new estimate of rho to do the quasi-differencing. And then I get to step 4, do that regression, and then I can go on to step 5 again, get a new set of error terms. So you can keep doing that until rho stops changing. So we say you iterate until convergence. That means you do that a few times and then rho stops changing. So you get a value of rho, you go up there, you plug it in, you go through all the steps, you get exactly the same value of rho back. So then you've converged on a solution. All right, so this is called, this procedure is called Cochran-Orcutt. So that first set of steps, the first 4 steps is Cochran-Orcutt. And then if you add in the 5th step that takes you back into the loop, it's iterated. Cochran-Orcutt. So iterated Cochran-Orcutt works for AR1. So if you have an AR1 error term, then you can use iterated Cochran-Orcutt to get yourself GLS estimates. Now, what if you have or you think you have AR2 or higher, AR3, and so forth? Well, in that case, there isn't a Cochrane-Orcutt procedure. You've got a couple of options. One option, you can use a nonlinear maximum likelihood model. So you can just specify it in R or Stata or one of these packages that you want to estimate a whole series of autoregressive parameters, and it will calculate them. Or, and these days what's more common is to use an autocorrelation consistent estimator. ACE. Autocorrelation consistent estimator. So what would this look like? Well, remember last time we talked about how these error terms, the residuals from the regression, they are consistent estimators of the OLS error terms. And so you can use these residuals to construct a consistent estimate of the variances of the beta terms, of the beta coefficients. And in fact, you don't need to specify how many lags you have. The formulas for the autocorrelation consistent estimator will give you variance estimates that are consistent regardless of how long the autocorrelation process is, as long as it's a stationary process. So the ACE estimator consistent for any lag AR process as long as it is stationary. The one that's mentioned in the book is called the Newey-West estimator. The Newey-West estimator, the way it works, if you want to think about it, it's using lags across the sample at varying lengths to construct all these covariances from the covariance of an error term and the one lag error term, the covariance of the error term and the two lag error term, the covariance of the error term and the three lag error term. It's estimating all of those just using the corresponding residual values through the sample. And then it constructs an estimate of the variance of the error term if it's constructed of this infinite series of covariance terms, and using the residuals to construct those covariances. And that's how it works. Obviously, we're not going to have to do that by hand because the computer does that. And in fact, in the textbook, he doesn't even really talk about this very much. He just mentions the Newey-West estimator. In assignment 4, you get a chance to use R to construct the Newey-West autocorrelation consistent estimator. And one of the nice things about the Newey-West is it's actually a hack estimator. It is heteroskedasticity and autocorrelation consistent. I'm having so much trouble writing. Autocorrelation consistent estimator. So it's really a very powerful estimation tool. There are a few of these. Newey-West is very popular in econometrics. The trade-off of, like, why don't we just always use this? The reason is, like heteroskedasticity, if you can find the correct GLS transformation, then you'll get the best possible variance estimators. In other words, the smallest possible confidence intervals, maximum t statistics. Nui West is consistent, but it may not be as efficient as the GLS estimator. The only problem is it's very hard to know if you've got the correct GLS estimator. And if you have a big long time series data set, you can't just assume it's AR1. You might have a very complex long-term autocorrelation process. So, and I tell you this from experience, having worked with time series data, if you're trying to find the GLS estimator, it can just be extremely time consuming because you're testing, you might have 12 autocorrelation terms in there, but then it may be that some of them should be 0, but some of them should still be in there. Maybe you're dropping a bunch of the shorter ones, but keeping some of the longer ones. It just takes ages, and you're never quite sure you've got the right one. So it's far more common now for people just to switch to a hack estimator like Nui West. And then if you got a large enough sample, that you're going to get close to as good a solution as with GLS. So for that reason, you'll do a Cochrane-Orr cut. It's nice to do it just to see how it works. It tends to converge very quickly, only needs a couple of iterations. And it works for the AR1 model, which is the most common form of stereo correlation. But in practice, if you go on to use econometrics in your daily life, you just get used to using things like Nui West or White's errors in the heteroscedasticity case. So that's all for this lecture. Next class, we're going to learn how to test for autocorrelation. And then that'll be all we need to do for this unit. So I will see you next time.